and Ralf Jung as the next speaker, who has been a key member of the IRIS project for many years and has been in Boston working with Nikola Sedovich and Franz Kasuk for the last 2 years officially, and I think the first year he was still based in Germany, but he's now in Boston, and he's going to talk about IRIS and Rust. Take it away, Ralf.
All right. Yes. Thank you, Leonard. Can you all hear me?
Yes.
Yep.
Great. And I hope you can also see the slides without any strange borders or something, frames that shouldn't be there.
Sounds fine. Looks fine.
All right. Yes, thank you for the introduction. Indeed, I will be talking about verification of concurrent software today. So the observation is that to make the most out of modern hardware, modern programs are increasingly concurrent. And sometimes they are concurrent with pretty catastrophic effects, as can be seen from this list of critical security issues that have been caused by concurrency bugs in just the last half a year. So what makes concurrent software so hard to get right? Well, let's look at a simple example. Here we have a small program that starts with a variable x that is initially 0, and then on the left, the thread will increment x by 3, doing it in 2 steps to model how this is actually usually executed. And then it asserts that the final value of x is indeed at least 3. And meanwhile, the thread on the right will do an increment by 2. Now, if we look at these 2 threads in isolation, it is fairly easy to convince ourselves that this assertion will always hold, because we're just incrementing x. However, if we actually run these programs concurrently, then we will very quickly notice that the assertion can indeed fail, because we might, but what happens in that situation is that the instructions of these 2 threads are interleaved in some way, and if we are unlucky and catch this kind of interleaving, then the increment by 3 on the left is kind of overwritten by the increment by 2 on the right, and we end up with 2 as the final value of x, and the assertion fails. So what this simple example demonstrates is that just naively doing thread local reasoning in a concurrent setting doesn't work. At the same time, just naively exploring all possible executions also clearly will not work, because there are exponentially many of these executions. So we can't just do like straight up exhaustive state space exploration. So what can we do instead? Well, maybe let's try going back to this idea of thread local reasoning, and let's try to be a bit less naive and a bit more clever about it. And that is the core idea of using separation logic for verifying concurrent software, where we can achieve thread local reasoning by keeping threads separated, which is reflected in this amazing proof rule from concurrent separation logic that is called the parallel composition rule. What this rule says is that if we have verified the left thread under some precondition P1 and postcondition Q1, and we've also independently verified the right thread under precondition P2 and postcondition Q2, then we can run both of these threads concurrently, and they will be correct under precondition P1 star P2, where the star operator here is the separating conjunction operator, and it is really the star of the show in separation logic, because what it roughly says is that P1 and P2 hold on separate or disjoint parts of the machine state. So for example, disjoint parts of the physical heap, which then means that L and R can execute without stepping on each other's toes, and we can verify them independently. So this basic idea turns out to be super powerful and has already been the foundation of a wide range of academic and industrial verification tools, and its application to concurrency has been awarded with the Goodell Prize a few years ago. So this is all nice and fine. However, there's a problem, and that is the major weak spot of separation logic is the problem of handling shared mutable state, as it comes up, for example, when implementing atomic reference counting, Michael-Scott queues, concurrent hash maps, any kind of these concurrent data structures. And that's hopefully not too surprising, because after all, we have specifically designed separation logic to separate the state that concurrent threads are working on. So now if they are working on the same state, well, that kind of separation doesn't work anymore. So what usually happens, what people usually do, is that they complement the idea of separation with another logical ingredient to account for sharing and for interactions on shared state. And that kind of ingredient is often called regions or state transition systems or protocols. Indeed, there's lots of different proposals for what the second logical mechanism could be, which leads to lots of different logics that are all or almost all derived from concurrent separation logic in the top right corner. So we have a wide range of possible and sound reasoning principles available for these kinds of programs, which on the one hand is great, But on the other hand, those all being independent logics has the big problem that proofs done in different logics do not compose. So this is a problem if you want to verify large software systems, because if you verified your queue and your hash map in different logics, you cannot actually put those proofs together in the verification of a larger system. So to make progress on this idea of verifying large systems, we need some way to compose these proofs. We need to find a unifying principle that can explain all of these ways of reasoning about shared state and also talk about its interactions. And so that is what we are proposing with Iris. And the key observation is that we don't even need a new logical primitive to do this. All we need to do is generalize this idea of separation from separating the physical machine state to separating some more application-specific notion of resources. And so by defining the right notion of separation and resources for different libraries, we can, for example, verify the queue and the hash map independently in Iris, and then compose those proofs together as part of verifying a large program. This turns out to be well enough that it has already...
You have a question.
Yes?
Yeah, so go back to the previous slide and you're talking about compose. Why do you need to compose proofs from different logics? I missed that.
Well, let's say we have proven, like we have some amazing result proven in one logic and another amazing result proven in another logic, and we want their different libraries. We want to use both of them in our verified software. So we need to put those proofs together.
You couldn't transfer the proofs?
I'm sorry?
You couldn't transfer the proofs from one logic to another?
No, they're running completely different. They're using completely different reasoning principles. The way that these logics talk about sharing doesn't really transfer from one logic to another. I mean, maybe there's a way to do that, but then it hasn't been done.
So when you compose it, do you end up in a third logic then?
I mean, that might be an option, to find the third logic and then be able to translate all of these proofs into that logic and then compose there or something like that. There's like, but what we are proposing instead is to just start out by doing all these proofs in the same logic.
Okay.
Okay, so this approach of using application-specific separation turns out to work well enough that Iris has already been picked up by industry. So, for example, Facebook has used Iris to verify a core part of the IPC mechanism in their VR microcontroller. And we've also seen quite a few uses in academia, for example, to verify file systems implemented in Go, to have a program logic for Camel, to verify the Scala type system, or verify C code, or various other verification projects. And one project that I will go into a bit more detail about later is Rust Belt, where we verified the safety claims of the Rust programming language using Iris. So overall, we've seen more than 50 publications that have used Iris one way or another to verify some software property, and almost all of these results have been mechanized in the Coq Proof Assistant. So this is then the plan for the rest of the talk. I will start by explaining how in Iris we use application-specific resources to reason about concurrent data structures. And then I will explain how in Rust Belt we've applied Iris to verify the correctness of the Rust type system. So let's get started with the Iris part of the talk. In this part, the idea is that I will have a simple, rather toy example to demonstrate how to use Iris. And that example will be that of a greatly simplified reference-counted object. So what is a reference-counted object? Well, the basic idea is we have some buffer on the heap that stores the data we care about. And then we also have a counter somewhere that tracks how many pointers currently exist to that data. So we might start out with one pointer, and a second pointer gets created. The first pointer is removed, and when the second pointer is removed and the count reaches 0, we know we can deallocate this object from the heap. So in a sense, this is a simple form of garbage collection. And so how do we implement such a reference-counted object? Well, the basic API that we are going to consider here is that we can increment and decrement the count, and we have a way to read the data feed. So in the simplified API, we cannot actually change data so that I can keep the invariant reasonably simple. For the increment operation, we need to increment that count field, and we need to do this in a way that avoids these kind of data races where the increments get lost that I had, the example that I had at the very beginning of my talk. So we are going to do this using the FAA, the atomic fetch and add operation, which is supported by most modern hardware and means that the value in the count field is just incremented by 1 in an atomic fashion without any issues if this happens in multiple threads concurrently. The decrement operation similarly uses FAA to remove 1 from the count. And then FAA returns to us the old value of the counter. And so if that old value is 1, so we just decrement it to 0, then we know we can deallocate. And finally, read just returns the current data field. And now our goal for this part of the talk is to prove that if we use this API in the intended way, there will be no use after free and no double free. So just basic memory safety, no functional correctness. But of course, to prove anything about this program, we need to start by stating the specification. We need to formalize this idea of using is the intended way, which with these program logics and Iris in particular being core logics, we do by having preconditions and postconditions in curly braces around the code that we want to verify. So in this case, the precondition is arc of x, which is an abstract predicate that we use to mean that we have the permission, or we own the permission, to use x as a reference counted pointer. And then the postcondition is also arc of x, but written twice, which looks a bit redundant. And indeed, it would be completely redundant if this would be a regular conjunction, like a normal logical conjunction. However, we are using a separating conjunction here. So what this actually means is that we have the arc permission twice, which is powerful because we could now, for example, spawn 2 threads, give each of them one of these arc permissions, and now these 2 threads could use x independently without worrying about what the other thread does. So there's a lot of very subtle things that are expressed very concisely by using the star operation here. So intuitively, what inc does is it generates a new arc permission. And so dually, what decrement does is it destroys one of these arc permissions. It requires arc in the precondition, and then the postcondition is just true. So any knowledge, any permissions and ownership you have is just gone. And then finally, the read operation also requires arc of x as a precondition, but then gives us back unchanged in the postcondition. So that is the specification that we want to prove. But before we can prove anything, we need to decide what even should this arc of x predicate be. Right? We need to define it, and we can start proving these autotrophs. But defining this arc of x is where things start to become interesting. Because usually in separation logic, we would define these things in terms of the points to assertion, which says that we own parts of the physical state. However, that would also express that we want to separate these different arcs along the physical state, which is just not what happens here, right? All of these pointers, x and y, are pointing to the same part of the heap. They're not actually pointing to independent parts of the heap. They're shared state here. So we can't say, oh, we have separation on the physical state. We need to find some other way in which these arc predicates are separate. And so this is where Iris comes in. What we do in these situations in Iris is that we make up a new kind of permission that we then use to explain the kind of separation that is going on. And at a very high level, I will get back to this in more detail later, the kind of permissions we need for arc are, on the one hand, a permission that reflects this count field and the exact current, tracking the exact current total number of pointers. And on the other hand, one permission for each of these pointers that exists somewhere out there in the program. So the general structure for one of these proofs in Iris is that we start by defining an application-specific notion of ghost permissions and the associated ghost theory that we will need for our proof. Then we find the right invariant that relates all of our ghost theory to the actual physical state. And then we perform the proof using that invariant. And finally, we justify the correctness of the ghost theory by picking the right resource algebra. So I will go into more details about all of these points for the rest of this section. To begin with, what is the ghost theory that we need for arc? Well, the ghost permission that we need is, first of all, we need one of these, we need this permission, which I call total count, which represents that the current count of x is exactly n. And this is a unique permission in the sense of that there exists exactly one total count permission per x in the entire proof. You can never have two of them. And on the other hand, we have this one count permission, which represents ownership of a contribution of +1 to whatever the current total count of x is. So we don't know the exact count, but we know that we have added 1 to that count. The laws that we will need to govern those permissions, so this what I call the ghost theory, are, first of all, we need to know that if we have the total count of x being n, and we also have a 1 count contribution to that count, then n must be at least 1. So hopefully that makes sense, because if we have contributed 1, then the count can't be 0. And the second ghost theory is the one that lets us change the total count. So what this says is that if we start out with the current total count being n, then from left to right, we can increment the total count from n to n+1 and generate a 1 count permission in the process. And reading the same law from right to left, we can decrement the count from n+1 to n and destroy a one count permission in the process. So with that ghost theory defined, we can now go ahead and define the invariant that we will need for our reference counter pointer. This invariant is where we'll finally see the points to assertion that you might have been waiting for ever since I started talking about separation logic. So in this invariant, we will say what actually is the physical state of this arg counter. Specifically, we say that the count field of x contains some value n, and that inside this invariant, we have ownership of this points to, meaning we have full control over what the current value of that count field is. And we also likewise have ownership of the data field, but for this simple example, we don't care about the values stored in that field. However, the invariant will not always own this count field or own this memory. After all, at some point, we want to destroy and deallocate the arg when it reaches 0, and then this ownership will be gone. So in the invariant, we have a second case where the n right ought to just be 0, and then there's nothing else to show. That is the physical part of the invariant. And then the second part of the invariant relates to the ghost permission that I've just introduced, where we will also say that inside this invariant, we have this total count permission, which controls exactly what the current count of like numbers of pointers to x is. And crucially, total count and the physical count field use the same n inside this invariant. So this keeps the physical state and the ghost state always in sync. That is what this invariant crucially enforces. Now, the last thing that we have to do, another more abstract way to think about this invariant is to think of it as a state transition system, where there is basically one state for each possible value of n. And then as we keep incrementing and decrementing this n, as we keep changing, so to speak, the witness for this existential quantifier, we transition back and forth in this transition system. Every time we go to the right, we use our total count update law from left to right and generate a one count permission. And every time we go to the left, we use the total count update law from right to left, and we destroy one of these permissions. That's some kind of intuition for this invariant. Now, the last step that we have to do is we have to draw a box around arginf, which is the Iris way of saying that arginf, the assertion arginf itself, is maintained as an invariant on shared state that all threads can rely on, but also that all threads have to maintain as they progress. So finally, we can now define the meaning of this arg of x predicate as being, on the one hand, ownership of a +1 contribution to the current counter of x, and on the other hand, knowledge that arginf is maintained as an invariant on shared state. With the invariant and the abstract predicate settled, we can now go to the next step of actually verifying our code. Concretely, we're going to look into verifying this for triple for the increment operation, which, remember, is defined as just a single atomic fetch and add operation. I will write down this proof in Hoare outline style. So basically, line by line, I would state what are the logical assertions that we have and transform them according to the rules of the logic, stepping over the code as necessary until we finally have managed to reach from the precondition to the postcondition. So let's start by making a bit of space. And the first thing we're going to do with our precondition is unfold it to learn that we have indeed a one count permission and also this knowledge of the arginf invariant. And next, we're going to observe that the fetch and add is an atomic operation. So basically, for the duration that it takes the fetch and add to execute, we can pretend that we are the only thread that exists on the machine. And so even though arginf is an invariant on shared state that other threads can also work on, because for one atomic instance, we can ignore other threads, we can actually pretend that we fully own this shared piece of state. We just have to make sure we give it back before any other thread can take their next turn. So this means we now have arginf, the contents of arginf fully in our precondition, which we can unfold now to be this, on the one hand, total count, and on the other hand, the big disjunction that represents ownership of the physical state. Now, next, we're going to use the first law from our ghost theory, which says that if we have total count xn, and we also have a +1 contribution to x, then n must be at least 0. So this way, we can rule out the n equals 0 case, which is important because we've just proven that the fetch and add here does not do a use after free. So that's quite relevant. We have shown memory safety of this increment operation. Now that we actually have an x.count points to in our precondition, we can justify executing the fetch and add. And the effect of that will be to change the value from n to n+1. But of course, now that we've changed the physical state, we have a problem because the ghost state, the ghost permission reflected in total count, still says the count's n. So we now have gotten our ghost state and our physical state out of sync. And so to continue in this proof and to reestablish arginf, we need to get them back into sync, which we do by using the second law from our ghost theory from left to right, where we can increment total count from n to n+1 and generate a 1 count permission in the process. So now total count is n+1, and the physical permissions are highlighted. But with all of that, we have now managed to reestablish the arginf invariant. So we've shown that all of the things we did here with fetch and add preserve that invariant, which is important. We are well-behaved citizen of this system that works under this invariant. So we can basically go back to justifying that the invariant is now shared again. Everybody else can access it again because it is reestablished. And what we keep after, what we can maintain after doing that are these 2 1 count permissions. And of course, still knowledge that arginf is maintained as an invariant. Because that is pure knowledge, we can duplicate it. So each of these argx that we have in our post condition will require 1 of our 1 count permissions. And then they both need to know that arginf is an invariant in this box. But that is just the fact that once it holds, we can duplicate it arbitrarily, so we can use it to justify our post condition. Okay, so that completes the proof of inc. I'm not going to prove the other functions here for lack of time. However, there's one problem still, which is that, well, we completed the proof assuming a bunch of axioms that are just posited to make some sense, or that just said we could have these laws about our ghost permissions. So how does that work? How are we sure that these laws themselves don't introduce logical inconsistencies? So this is where we get into the third part of what I mentioned to be the Iris proof plan. Basically, the way we do this, and I'm only going to give a very rough idea here, is that we show that these resources we've talked about, total count and 1 count, have a composition operation that defines how the resources of multiple threads have to be composed. And this composition operation satisfies a bunch of algebraic properties, which are basically those of a partial commutative monoid. We call it resource algebra. And we've shown that any kind of resources that is a resource algebra that has a suitable composition operation satisfies a bunch of logical laws that we have in Iris. So these 3 laws that you see here, and one more that's even less, even shorter, are laws that we've shown once and for all. We've proven them for any possible resource algebra. And now as a user, all you have to do is pick an arbitrary resource algebra, show that it is indeed a resource algebra, and then you get all of these logical laws for free. And so by picking the right resource algebra, we can derive from these laws the theory that we need for our reference counting proof, but also the theory that we might need for any other kind of proof, if it would have been a queue or a hash map or a reader-writer log or something like that. In fact, we can also derive from this the theory that governs the reasoning principle for physical state itself, and by doing some more interesting high-level mathematical work, also the theory that governs invariance. So invariants in Iris are also just another kind of resource algebra. The common idea of monotone state, which you can often find in concurrency verification, is also just an instance of this general pattern. And finally, the complicated reasoning principles that have been taken as primitive and prior logic that are the foundation for a whole bunch of interesting case studies in those logics can also be derived from resource algebras. So where in logics like carousel, ICAP, and Tada, we had complicated proof rules that were directly at the basis of the logic and had to be justified by doing proofs in the model of those logics, and those were complicated proofs. We can now have those same reasoning principles, but we can derive them at a much higher level of abstraction from our notion of resource algebras. And crucially, because they are now all derived from the same framework, we can compose them in the same proof. So no matter which of these resource algebras one part of your proof use, the other parts of the proof can use other resource algebras, and this will all compose nicely. So this is the sense in which separation of application-specific resources is all you need to do your proofs in Iris, and everything I've said here has been formally mechanized in the Coq proof assistant. Are there any questions before I move on to the second part of the talk?
Question for you. So the program that you showed originally with the 2 threads running concurrently and the assertion being violated.
Yes.
Could you prove that the final value is at least 2? So that's an example of shared mutable state.
I mean, I haven't done the proof because it's not a very obvious, not a program we usually write. But yes, we could prove that. Yeah.
No, but what do you use separation-wise to do that kind?
I mean, you would basically reflect that. Well, so one of the things that we can encode by using the right resource algebra is the idea of a monotone counter. And so this count is not entirely monotone because it can be 3 and then 2, but we can prove that once it is at least 2, it will never be less than 2. So that is the kind of you can almost think of this as a state transition system, which we can also encode as a kind of resource algebra. And so we could prove that all of the code in this program satisfies the invariant that once the counter is at least 2, it will remain at least 2. And can also prove that in both threads, when they are done, the counter is at least 2. And so in the end, then that means that in the end it will also be at least 2.
Okay, but that's a kind of conventional weak agrees proof.
I mean, we can encode this kind of reasoning in Iris by picking the right resource algebra. So you don't have to do weak agrees where you actually look at like the derivations of your other threads. We can do this in a modular way by picking the right invariant.
Okay, go ahead now.
Okay, thanks. All right, so in the second part of this talk, I want to talk a bit about Rust. The idea here is that I've just demonstrated how we're using Iris to verify a fairly simple specification for a very simple piece of code. And the proof wasn't like entirely simple. So you might wonder, does this even scale? Can we use Iris to prove anything interesting about anything real? And I would like to convince you that yes, we can, by talking about what we have done with Iris, proving things about Rust. So what makes Rust interesting is that as a programming language, it combines on the one hand low-level control, like you might be used to from C or C++, with on the other hand strong high-level memory safety guarantees like use after free and thread safety guarantees like absence of data races. And moreover, Rust is widely used by a lot of big companies and open source projects, and is even on its track to become officially used in the Linux kernel for some of the for the first device drivers fairly soon. So this is clearly a very interesting and up-to-date language. And the way it achieves all of these properties, or at least one core ingredient to that, is a fancy type system. So let me explain a bit how the Rust type system works. The core idea of the Rust type system is that it rules out the unrestricted combination of aliasing and mutation. And the mechanism through which it achieves that is the idea of ownership. So in general, in Rust, if you have a variable x of type t, then that means that you fully own this memory where x is stored, and no other part of the system, no other thread can even read from that memory. It's completely yours. So there's no aliasing going on, which means you're allowed to arbitrarily mutate and even destroy that object. This is a very powerful ingredient to have in your type system, but it can also be fairly limiting. So Rust combines this with the idea of borrowing, where you can temporarily borrow access to some data to another thread or another function. And then when the lifetime of the borrow ends, ownership flows back to you. And borrows come in two shapes to represent these two sides of the coin, where they can be either aliased or mutable, but never both. So this gets you very far. This is a really expressive type system. However, inevitably, in a large program, at some point, a situation will come where you actually do want to have some alias mutable state. So what is the answer that Rust has to that problem? Well, let's look at a simple example. By considering a Rust program that uses this arc type from the standard library, which is indeed a full-fledged version of the kind of simple reference counting example I used in the first part of this talk. So what this program does is it starts by creating a new reference counted object that stores the number 42. And then it calls clone, which is the Rust name for the increment operation. So after the setup phase, this little diagram shows what the situation in memory looks like. Then we spawn a thread, which will run in the background, and we'll use the xclone pointer to read the current value, the current data field, and then it will drop xclone, which will decrement the reference count. And then meanwhile, concurrently in the main thread, we do basically the same thing using the x pointer. Now, this is a fairly simple program, but what's interesting about it is that actually there is alias mutable state here, because x and xclone both point to this count field, and when the first thread drops it, it will be mutated, it will be decremented from 2 to 1. So somehow something has to be going on here where Rust actually lets us write shared mutable state. And so what happens here under the hood is that this seems to completely violate the idea that we can't have alias mutable state in Rust. And so what happens under the hood is that Rust has this idea of unsafe code. So basically, when you're writing code which you think is correct for reasons that are too tricky for the compiler to check, you can use unsafe blocks. And then inside those syntactically marked blocks, there are some extra operations that you have access to, which the compiler would usually not let you do, because the compiler can no longer check itself that you're actually doing everything correctly. However, the claim of the developers of this Arc library is that while we have to trust that the implementation of Arc is done correctly, we can still make sure that all users of Arc are correct, and we don't have to trust any of the users of Arc. So what do I mean by that? Well, let's look at an example of using Arc incorrectly by changing our program and reordering the two operations in the background thread. So we will now first drop xclone and then try to read the data field. This is a buggy program because when we drop xclone, that decrements the reference count, and it might now actually be 0, and so deallocate the object, which would mean now in the next line, printing the content of the data would be a use after free. However, lucky enough, the Rust compiler notices this problem and gives us a compile time error, because when we drop xclone, we actually give away ownership of xclone, so we can no longer use it to read the data feed afterwards. So the general claim of a library like Arc in Rust is that any way of interacting with this public API will still have the full suite of memory and thread safety guarantees that Rust provides. And we call this API safety. You can almost think of it as even an adversarial client, as long as the client does not itself use unsafe, cannot break the data structure invariants. And it's not just Arc that does that. This is a common pattern in Rust programs, where we have a large body of well-typed code that contains the application itself and most of its libraries, all of the business logic. Most of the code is in that fragment. But then in particular, at the bottom of the stack, where you have your interesting high-performance, low-level libraries, or the concurrency primitives or things like that, then there is unsafe code that is wrapped in a safe abstraction. And these safe abstractions, for example, in the case of mutex, will make sure that you can never forget to take the lock if you want to access the data. It's impossible to access the data without actually holding the lock at the same time. At least that's the claim, again, of the developer. So our goal with Rust build now was to formally prove all of those safety claims. We not only want to show that the Rust type system itself is type safe, we also want to show, or want to have the methodology to show, that these standard library components, and also components developed by other Rust developers, are API safe, are a safe extension of the Rust type system. And so I want to briefly explain why that's a really hard thing to prove, because basically what we're showing is that every well-typed program that uses Arc will not crash when it runs. And by no crash here, I mean execute memory safely. So it can still like abort in a safe way, but it can't have use after freeze or data races or anything like that. So, yes?
So does this include, I mean, if you omit the drop in the thread, is that also API unsafe?
So if you omit the drop, Rust will actually insert it automatically. It's like in C++, these structures are called implicitly. I just wrote it for like to show what happens. However, it is possible to have memory leaks in Rust. Rust does not guarantee memory leak freedom. It is usually you have to work a bit to get memory leaks. If you don't do anything strange, memory will be deallocated, but that is not a hard guarantee the same way as memory safety and thread safety are. Okay, so what makes this theorem here interesting is that it is a theorem that is universally quantified over programs, which is quite different from the usual kind of verification problem that we have, where verifying a concrete whole program, or at least a concrete library that is embedded in some larger program. And to make it even more tricky, this well-typed program might not just be using Arc, it might use Arc in combination with arbitrary other API-safe libraries that we don't even know exist yet, right? We don't want to reprove everything every time a new library comes along. So these proofs have to be compositional and done in isolation, so that I prove Arc and I prove mutex completely independently, but then arbitrary ways of using them together still have to have all the safety guarantees. So that's what we're shooting for here. How are we doing that? Well, we have to start by even defining what are these well-typed programs. So we have to define a programming language that models Rust. I'm not going to talk much about the language. And we have to define a type system that models the Rust type system. And this type system has some of the normal types you might expect in all the usual type systems, like base types. And then it also has 3 kinds of pointer types that correspond to the 3 kinds of ownership we have in Rust: full ownership, mutable references, and shared references. And then it has a whole bunch of other fancy type system features, which make it like a full-fledged type system. It has recursive types, sum types, product types, function types, so it's fully higher order, all of these things. Once we have our grammar of types set down, we can now define the typing relation, which basically is a formal way of saying what actually is the compiler checking when it type checks your code. And so we use the statement spelled turnstile C to mean that the code C is well typed and passes compiler checks without using any unsafe code internally. So this without unsafe is important because, of course, we're not making any promises about code that uses unsafe. At least the compiler is not making any promises about that. So, for example, we can now state that the Arc client we wrote is completely safe by saying that, or at least it's well typed and doesn't use unsafe by saying turnstile Arc client. However, at the same time, turnstile Arc does not hold because the implementation of Arc internally uses unsafe. However, this puts Arc in the same bucket as all sorts of completely bogus code that actually violates safety guarantees. So we have to find some way, we have to express some way in which Arc is still safe, even though it doesn't satisfy this condition that we can formalize that models what the Rust compiler is doing. So this is where we are following the idea of semantic typing, which basically means we define a second typing relation that we write with a double line turnstile. And so this double line turnstile of C means that the program, the code C, behaves safely on well-formed inputs. So this is in contrast to the syntactic typing relation, the single turnstile C, which says that if we just go line by line over the source code, that will satisfy the type checker. The second notion is completely automatic, and it's just there's an algorithm that can do this check. It's what the Rust compiler does. Whereas the first notion is a lot more flexible, but way undecidable. So let me give an example. Here we have a small program that says if false, then true plus 3.5, and if you give this to the type checker will be like, what the heck are you doing? You're adding a Boolean and a floating point. This doesn't make any sense. Your code is clearly not well typed. So this is not in the regular single turnstile relation. However, semantic typing would say, well, if we run this code, nothing ever actually happens because the bogus part is inside a dead branch. It will never execute. It has no effect whatsoever on the observable behavior of the program. So this code is actually fine. It's semantically well typed. So this is the sense in which the semantic double turnstile notion is more clever than the syntactic notion. Now, of course, the problem is actually formally defining semantic typing for a language as intricate as Lambda Rust with all these features of ownership and borrowing. And this is where finally Iris enters the picture. So in particular, to define this notion of semantic typing, we have to define this notion of well-formed inputs, which boils down to stating representation invariants for all types in the type system, as well as the implicit global invariants just upheld by the context itself. And to state those invariants, we need the full expressivity of Iris. Let me show you some examples. I will use the notation rep tau v to mean that the value v satisfies the representation invariant of type tau. And so if we now consider, for example, the type of owned pointers, then we can say that some location or pointer value L satisfies the representation invariant of an owned pointer to tau if L points to W. So we're now using the separation logic points to assertion to assert that we actually exclusively own the memory that L points to memory, the value that L points to. And moreover, this W L points to itself recursively satisfies the representation invariant of tau. So by using this idea of separation, of like points to assertions and separation logic, we can very concisely express the concept of an owned pointer from Rust, because we have chosen Iris as the logic to express our representation invariants. If we had not used Iris, or if we had not used a separation logic at least, this would be a lot harder to make precise. Now, owned pointers are still fairly simple. Things become interesting and complicated once you consider borrowing. So at first sight, this doesn't look that bad. The representation invariant for mutable references looks almost the same as that for owned pointers. Indeed, the highlighted parts are exactly the same, which should hopefully make sense because the idea of a mutable reference is that temporarily, for some lifetime, you actually basically have full ownership of that memory. However, then around this highlighted part, I've written this ampersand kappa full thing, which looks a bit like a Rust type, but actually on the right-hand side of the definitions sign here is connected from the lifetime logic. So the lifetime logic is an extension of separation logic that we've developed for Rust Belt, which equips separation logic with the idea of borrowing ownership temporarily. And this is indeed a very non-trivial extension. We had to go deep into the bag of tricks that Iris offers to be able to verify that the lifetime logic is correct, but we've completely done this on top of Iris. We've basically encoded these lifetime logic principles inside Iris. But once we did that, we now have the toolbox basically to go back to this complicated theorem that I said we wanted to prove, where the theorem that was universally quantifying over all possible code. So let's look what we have to do for that theorem. We are given an arbitrary Arc client, and we will assume that the client code, that is the unknown code that we quantify about, is actually well typed and doesn't use any unsafe itself, right? So that was our assumption. So we can assume turnstile Arc client. And our goal is to show that if we put Arc client together with Arc, you can think of the plus here as a form of linking, then this entire program will not crash in the sense of it will be memory and thread safe. How do we do that? Well, we start by proving that Arc, the other part of the code we are running, is semantically well typed. We have to show that it satisfies the semantic double turnstile, the clever notion of typing. And this is essentially a much more elaborate version of the proof that we've done in the first part of this talk. And we are making heavy use of application-specific resources to verify that this concrete library actually satisfies its semantic notion of typing. And then we have to show a few more other theorems to put it all together. So first of all, we have to show that syntactic typing implies semantic typing. Basically, our clever notion of typing actually should better be strictly more clever than the simple thing the compiler does. And in that proof, the lifetime logic is very important. Secondly, we have to prove that semantic typing composes, as you would hope from any kind of type system, if you've shown that two program components are well typed, and if the types match at the interfaces, then the program links together should also be well typed. And finally, we have to show that the semantic type system is actually type safe, as in it implies that programs execute safely, which is a result that we directly get from Iris being a concurrent separation logic, so it is more than able to show memory safety and thread safety of concurrent programs. And crucially, these last three theorems that I mentioned that we have on the left here, we only have to show them once. We don't have, these are not specific to Arc or Arc client, they're just general properties of our typing relations. And so once we've done that once, we never have to look at it again, which means that the one thing that is left to do each time we consider whether a library like Arc or Mutex or VEC is actually API safe is that library itself. All we have to do is show that the unsafe pieces of the code are API safe. And then we get the result, which says that arbitrary safe Rust code that composes these internally unsafe libraries will also satisfy all the safety guarantees. So this is the main result of Rust Belt. So to summarize, what we've done with Rust Belt is we have defined Lambda Rust as a model of Rust and its type system. And we've carried out a semantic type soundness proof of Lambda Rust based on this lifetime logic, a non-trivial extension of concurrent separation logic with the idea of borrowing. And then we've established API safety of a number of key libraries for shared mutable state that you can find in the Rust standard library and beyond. And we've even found a bug in one of them. And some follow-on work, some of my colleagues have then extended this work to consider a more realistic model of memory in a concurrent program, so-called weak memory. And as part of that, have found another bug in Arc. And as part of all of this, we've also worked, all of this has been mechanized in the core proof assistant, of course. And as part of this, we've also worked a lot directly with the Rust community to get a better understanding on our side and on their side to help discussions about what even is this notion of API safety and how do we think about various situations where libraries are sound or not sound, or combinations of libraries are sound or not sound. So this is something that the community itself is very interested in, and it's been very interesting to have those discussions with the upstream developers. So this is all that I brought today. When you use Iris to verify your concurrent program, then separation is all you need. And the work that I presented today, of course, is not just mine. There's a lot of people that worked on this, and you can find their names on the slides. Thank you.
Excellent. Thank you very much. Questions?
I have a question, Ralf.
Yeah, go ahead.
Yes.
So the syntactic type system, is that parametric in the API? You know, for every new thing like Mutex or something like that, you have to change the type system.
I mean, we're not changing, when you implement Mutex, you're also not changing the Rust type system, right? Like, you're not changing the compiler, you're just writing a library. So it doesn't even need to be a parametric. The syntactic type system is fixed.
Okay, so it's what you have is that because you fix the API and the unsafe code is safe relative to the API, any API pattern usage, the syntactic type checking is adequate.
So I'm here about half of what you're saying is arriving here. I'm not quite sure what the question is, but the point is that these like mutex and arc and all of these things, they are doing interesting unsafe things internally, but their public API is entirely safe, or at least the part we care about is safe, and is expressed using the standard Rust types, right? That's the only way it can work. So the types of arc are carefully chosen so that we're using ownership and lifetimes to ensure that all the ways of interacting with that library following the standard rules of the Rust type system are safe. So for Lambda Rust, we have to only formalize those standard rules of the type system once, and then they remain fixed as new libraries come along. Now, an interesting question is whether those rules we formalized are actually the same ones as what the compiler really does. And the answer as a no, unfortunately, is no. There were some mistakes that we made in trying to model those typing rules, because like the Rust compiler is many thousand lines of imperatively implemented like data flow analysis to do the borrow and lifetime checking. So in some future work, I would like to get like have a type system which we can formally relate to the actual analysis done in the compiler, but that's a separate question.
Essentially, the composition theorem is just saying that the unsafe code is syntactically type safe at the API boundary.
Well, it's not syntactically type safe; it's semantically type safe, as in which is a type system that has all the same rules as a syntactic type system, but it can also accept a bunch of code that syntactic type system would not accept, like in this if false example that I had. Right? The semantic type system would say this is fine.
Yeah, but you only apply the semantic type system internally to unsafe.
Yes. The semantic type system can only be applied by hand, or maybe at some point we can develop some amazing automation for that. But for now, semantic typing is very complicated and has to be done by hand. So you only want to do it for unsafe code because it's a lot of work. So whenever you can use syntactic type system, you want to use that because it's an easier way to get the same result. Like syntactic typing implies semantic typing. So basically, the Rust type checker is an automated theorem prover for syntactic typing, which then implies semantic typing. So if that works, it's good enough. But for arc and mutex, it doesn't, and then we need to do some work by hand.
The question I was asking, you had the proof rule that gave you the composition.
Yes.
So that step isn't something deep. It's something.
So this is fairly well. So really, these two together are kind of one big proof where you essentially show you start with your syntactic type system, which has a whole bunch of these single turnstile things in it. And you take each of your typing rules and you make all single turnstiles double turnstiles. And now that's a theorem in Iris, and you prove all of those theorems. So basically, you show you figure out some invariants, you define them as your double turnstile, and then you show that all of the typing rules are kind of correct with respect to those invariants. That's a standard approach of semantic typing or logical relations. And if you do that, you get both these results here. You get both that it composes and that syntactic typing implies semantic typing.
Thank you.
Is there a programming recommendation or so in Rust that tells people that unsafe code should rarely cross API boundaries, or how common is it that unsafe areas are sort of nicely isolated?
They are usually isolated. I mean, generally speaking, people in Rust care about safety. That's one of the reasons why people use Rust. So library authors generally promise, and also everybody expects library authors to promise, that the safe parts of their library satisfy this kind of API safety notion. And so for library authors to be able to promise that, they have to be able to be sure of the correctness of their code, which then naturally leads to actually having this kind of reasonable compatibilization. But of course, these libraries often also expose some unsafe APIs, and then those need careful documentation for what are the extra preconditions, postconditions that come along with these. And there is a discipline in the kind of more important parts of the ecosystem, so to speak, that every time you write an unsafe block, you justify why that unsafe code is correct by stating kind of what are the preconditions you need and where do they come from.
But the compiler doesn't check that.
No, this is all just...
There may be analysis tools, but not the standard compiler.
So far, there's not even any analysis tools. So far, this is just English. But of course, there is like longer term, it would be great to have more tools for that.
Okay, thanks.
Peter has a question.
Hi, Ralph.
Hi. I can't see people, unfortunately, so I never know who's speaking.
Peter,
Hi, Peter.
can you comment on the relationship between, or explain the relationship between the Lambda Rust that the proofs are about and Rust?
Rust?
Actual Rust.
Oh, well, ideally, there would obviously be some kind of soundness there. The problem is that to even state that theorem, we would need a precise specification for actual Rust, which doesn't exist yet. But I'm involved in the teams that are working towards such a specification. So once such a specification exists, we will hopefully be able to update or redo or something Rust-spelled to work against the actual like operational semantics that is specified for Rust. But so far, this is not possible because there is no such thing. As far as I know, we are reasonably faithful. I mean, obviously, we assume sequential consistency. We have a notion of non-atomic accesses. So the data race part should work out that way. But the main thing that we don't have in this work is Rust also has a lot of restrictions for what kind of aliasing you're allowed to have. So I have other work that looks into that. It's called stacked burrows. But this is not integrated with Lambda Rust or Rust-spelled. So that's kind of a mismatch there. And actually would have to also prove that all these libraries are following the aliasing rules, and we haven't done that yet. Because the aliasing rules are not finally decided for Rust yet. Stacked burrows is a proposal, but it has a bunch of problems, so it's not going to be the final version that Rust will actually use.
Okay.
Thanks, Ralph.
All right, thank you very much.
All right, thank you for having me.